Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into a place that is, paradoxically, both the darkest and the most illuminating of all cosmic destinations, black holes. They are not merely cosmic oddities, nor only devourers of stars. They are in many ways the universe's hidden map of time and space. But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe, only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the places we gather from, each in our own little slice of time. Now, feel free to dim the lights, maybe turn on a fan for a soft background hum, and let's gently begin our journey together. And if your mind begins to wander, that's perfectly fine. Let it drift. We'll still be here, quietly unfolding the story. So then, black holes. Even the phrase itself carries a hush, doesn't it? It sounds less like an astronomical object and more like a secret, a whisper of something you're not supposed to know. In the most straightforward sense, a black hole is a region of space where gravity has grown so strong that nothing, not even light itself, can find the strength to leave. The boundary of this region is called the event horizon, a kind of one-way curtain. Step across and no path leads out again. That's the clean definition, but it hardly captures the strange mixture of awe and discomfort these objects inspire. You might picture them as dark spheres floating in space, but in truth they are less like objects and more like conditions, places where the very structure of space and time folds in on itself. The idea is older than you might expect. Long before Einstein bent the universe with his theory of relativity, there were thinkers who wondered whether a star could become so heavy that even light could not escape. In the late 1700s, John Michel in England and Pierre-Simon Laplace in France proposed exactly that. They didn't call them black holes, of course. They imagined dark stars, hidden not because of their violence, but because their gravity imprisoned their own light. The notion faded into obscurity for a while, not least because no one could conceive of actually observing such things. After all, how do you see something that, by definition, does not shine? Fast forward a century and a half, and Albert Einstein writes down his general theory of relativity in 1915. His equation suggested that space and time are not rigid backdrops, but pliable fabrics, bending under the weight of matter and energy. Almost immediately, another scientist, Carl Schwarzschild, found a solution to those equations that described what we now call a black hole. To Einstein himself, it seemed like a curiosity, a strange corner case unlikely to be realized in nature. For decades, many physicists treated the concept with suspicion. Surely the universe would not permit such extreme objects. Surely nature would find some gentler way. But the universe, as it often does, turned out to be less concerned with our comfort than with its own rules. Collapsing stars, galaxies swirling with hidden mass, the detection of cosmic X-rays, all pointed back to the reality that black holes were not only possible, they were inevitable. Still, for a long time, black holes carried with them a sense of paradox. From a distance, you might see matter fall toward one and appear to freeze, time itself slowing to a halt at the edge. For those plunging in, however, time would continue as usual, carrying them beyond the horizon to a place no observer could ever describe. This clash of perspectives unsettled many early physicists. Could such contradictory stories both be true? The answer, softly but firmly, is yes. And here is where black holes begin to show their importance. They're not only destinations of collapsing stars, not only dramatic endings in the lives of suns, they're also meeting places for our most successful theories of the universe. General relativity, which governs the cosmic and the massive, and quantum mechanics, which governs the tiny and the subtle. These two frameworks, usually content to reign over different kingdoms, are forced into the same chamber at the heart of a black hole. It is here, and perhaps only here, that the universe insists we reconcile them. You might say black holes are the universe's stern teachers, assigning us the homework of unification. If this all sounds intimidating, don't worry. Tonight, we're not rushing headlong toward equations. We're strolling. We will drift slowly past the history, the paradoxes, the whispers of radiation, the shimmering hints of holograms, and the echoes of colliding giants that send ripples through the fabric of space-time itself. Along the way, we will pause often, noticing how these distant mysteries reflect familiar experiences. How falling into a black hole is not unlike watching the last drop swirl around a bathtub drain. How time slowing near its edge is not so different in feeling from watching a candle flame seem to stretch as your eyes grow heavy. How information scrambling within one is reminiscent of a library reduced to ash, its letters scattered yet somehow not entirely gone. And perhaps most importantly, we will allow ourselves to feel something of their strange beauty. Because for all their darkness, black holes are not monsters. They are maps. Maps drawn not with ink but with gravity, mapping how time and space themselves behave under pressure. To learn about them is to trace the outlines of reality itself, to glimpse where the fabric begins to crease and fold, and to realize that even in the deepest night, the universe is still offering us a guide. So, as you rest back now, let your breath slow and your body settle. Imagine the quiet of space, not as a fearful void, but as a calm sea of stars, each light a companion. Somewhere among them, invisible yet real, black holes wait, not to devour your thoughts, but to invite your curiosity. Tonight we begin not by solving them, but by letting their mystery keep us company. And as we step gently toward their horizon, know that there is no rush. The story unfolds slowly, patiently, as though the universe itself were whispering, "Take your time." Imagine, if you will, standing on the edge of a river. The water flows gently at first, rippling and curling over stones. Then, as you walk downstream, the current quickens. Before long, it becomes a rushing torrent pulling at your legs. Eventually you notice that just ahead the river disappears into a mist. There is a waterfall, and once the water passes a certain point there is no turning back. That moment, the point of no return, is a helpful way to picture what physicists call the event horizon of a black hole. It is not a surface you could touch, nor a wall that resists you. It is a boundary written into the geometry of space itself, a quiet line in the universe that divides what can escape from what is forever hidden. Now, here is where things grow stranger. From the outside, if you were watching a friend drift toward this boundary, you would see them move more and more slowly as they approached. Their clock ticking faithfully on their wrist would appear to drag, each second stretching longer than the last. Light leaving their body would grow redder, fainter, until eventually it would vanish altogether. To your eyes, it would seem as though they never quite crossed, as though they froze at the edge. Time itself for them would appear to grind almost to a halt. This unsettling vision was once known as the paradox of frozen stars, and for decades it kept scientists uneasy. But here is the twist. From your friend's perspective, there is no freezing. Their clock ticks on as usual, their heartbeat steady, their thoughts flowing without interruption. They do not feel time slowing, nor do they notice anything extraordinary as they pass the horizon. For them, the fall continues naturally, as though nothing special happened at all. They would slip past the boundary in silence, never able to turn back or send a final signal, but never sensing any sudden barrier either. Two stories, both true, told from two different vantage points. One from the outside, where time seems to stall. One from the inside, where time flows normally until the end. It is a reminder of something Einstein taught us. Time is not a single universal rhythm, beating the same for everyone, everywhere. It is local, personal, woven into the space around you. Near a black hole, where gravity is immense, those personal clocks disagree profoundly. What feels like moments inside may appear as eternities outside. It is almost as if the universe itself cannot quite settle on a single melody, but instead allows many instruments to play at once, each with its own tempo. You can sense something of this even without visiting a black hole. When engineers design the GPS system that guides your phone or your car, they must correct for time running differently in orbit than on Earth. Satellites higher up in weaker gravity experience time ever so slightly faster. The difference is tiny, nanoseconds each day, but left uncorrected, it would cause your location to drift kilometers in a matter of hours. In everyday life, time feels solid, absolute. In the cosmos, it is elastic, stretching and contracting under the pull of gravity. Black holes are simply the most dramatic examples, pulling on time until it becomes almost unrecognizable. To picture what it might feel like to fall towards such a horizon, imagine riding an escalator that never ends. At first, you glide easily downward. The world around you seems familiar, manageable. But the further you go, the more the escalator tilts, until at last you're no longer standing but tumbling headlong, unable to stop. To those watching from above, it looks as if you are trapped on the last few steps, crawling in slow motion, your descent delayed forever. But for you, the plunge is unstoppable, a journey that completes itself whether the outside world acknowledges it or not. Inside this mystery is a quiet lesson. Perspective matters. What is frozen to one is flowing to another. What seems eternal from the outside may feel fleeting within. We live with gentler versions of this in daily life. Think of how a child experiences a single year. It feels endless, packed with firsts and discoveries. To an adult, a year slips past almost unnoticed, a page fluttering by in the wind. The time is the same, measured by the same Earth circling the same sun, yet our experiences stretch or compress it, changing its texture. A black hole is the cosmic extreme of this relativity, a place where time itself becomes relative not just in feeling, but in physics. Physicists once found this unbearable, this clash of accounts. If something freezes at the edge for one observer but passes smoothly for another, which story is the truth? The answer, softly but firmly, is that both are. The universe has room for more than one truth when it comes to time. Each observer carries their own thread of reality, and those threads do not always align. Rather than breaking the fabric, this patchwork is the fabric. Reality is not one story told by a single narrator, but a chorus of voices, each keeping time in its own way. Perhaps that is why black holes feel both unsettling and magnetic. They remind us that the universe is not obliged to be intuitive. They reveal that our assumptions, that there must be a single clock, a single unfolding, are comforts we have wrapped ourselves in, not laws the cosmos follows. At their edges, black holes whisper that time is flexible, local, and deeply strange. They invite us to step closer, to let go of certainty, to accept that reality may look different depending on where you stand. And so, falling toward a black hole is not just about gravity, it is about perspective. It is about the quiet recognition that truth can wear more than one face, that the same descent can be frozen silence from one view and steady motion from another. Like standing at the edge of a great waterfall, we can only watch the spray and listen to the roar, knowing that once the water crosses the brink, it has entered a world we cannot follow. The fall is not the end of the story, but the beginning of a deeper one, written beyond the horizon where time itself begins to blur. When you first hear the phrase black hole, it may feel like a footnote in the vast book of the universe, a curiosity, dramatic perhaps, but tucked into the margins, rare, distant, and dangerous. Yet the more we learn, the more we discover that black holes are not margins at all. They are punctuation marks written boldly into the cosmic story. They are commas, pauses, and sometimes full stops in the sentences of stars, and without them the story would not read the same way. To begin, let's remember what happens when a massive star comes to the end of its life. A star is not a still object, but a balance, a constant push and pull. Inside, nuclear fusion produces light and heat, pressing outward. Gravity, that quiet sculptor, presses inward. For millions or even billions of years, these two forces keep the star in balance, as steady as a candle flame sheltered from the wind. But when the fuel runs out, the balance tips. Gravity wins. The star collapses inward with unimaginable force. If the star is heavy enough, 3 or 4 times the mass of our sun or more, nothing can stop the collapse. Not even the pressure of atoms themselves, and what remains is a black hole. In that sense, black holes are the natural destiny of the universe's giants. They are not rare exceptions, but expected endings. Like oak trees dropping acorns or people eventually leaving footprints in the sand, stars of a certain weight simply end this way. To study them, then, is not to look at strange anomalies, but to look at nature following its own path. Yet their importance does not stop with stellar deaths. At the centre of nearly every galaxy, including our own Milky Way, lurks a supermassive black hole millions or even billions of times heavier than the Sun. These giants shape the galaxies that circle them. Their immense pull helps organise the orbits of stars. Their bursts of energy, when they feed, can regulate how new stars form. You might say that black holes are gardeners of galaxies, pruning and shaping with invisible hands. Without them, the universe would likely look very different, more chaotic, less structured, a forest without order. But perhaps the deepest reason black holes matter is that they force us to confront the unfinished business of physics itself. For over a century, general relativity has described the large-scale universe. Planets moving in curves, light bending around the sun, the expansion of galaxies across cosmic time. Quantum mechanics, on the other hand, has described the very small, atoms, electrons, the buzzing of particles that seem to flicker in and out of existence. Each theory works beautifully in its own realm, and yet, like two brilliant musicians who never quite agree on the rhythm, they fall out of harmony when played together. Black holes are the stage where both must perform at once. The mass is immense, bending space-time to the breaking point. At the same time, the region is small, where quantum effects become impossible to ignore. Relativity says one thing, quantum mechanics another, and neither alone can describe what is truly happening inside. To understand a black hole fully, we must find a theory that unites both. In this way, black holes are not only cosmic objects, they are invitations. Invitations to physicists to finish a project begun long ago. The search for a unified picture of nature. This is not a dry academic puzzle. It is a mystery with real weight, and not only in a mathematical sense. Imagine two maps of the same land, one drawn by a geographer, one painted by an artist. Each captures something true, each useful in its own way. But lay them side by side, and you notice the rivers don't quite line up, the borders don't quite match. You suspect there must be a deeper map, one that reconciles them both. That is what black holes whisper to us. They hint at the deeper map, the one where space and time and particles and forces all fit together. It can feel strange, almost ironic, that the darkest places in the universe may also hold the brightest clues. But this is often how nature works. Seeds are hidden underground. Pearls form inside rough shells. Some truths are concealed, waiting for patient eyes to notice. Black holes may be the universe's way of telling us that light is not the only teacher. Darkness, too, has lessons to share. Of course, our fascination with black holes is not only theoretical. They remind us, too, of our own relationship with time. Just as an outside observer might see matter freeze at the horizon, we often look at our own lives and feel moments freeze. The last time you saw someone, the instant of a goodbye, the weight of an event that seems to hang forever in your memory. And yet, from within, life keeps flowing. The parallel is not perfect, but it is suggestive. The cosmos often echoes our inner experiences, as though reminding us that we are not separate from it, but expressions of the same fabric. Black holes matter because they are both distant and intimate. They shape galaxies light years away, and they shape the very equations that let your phone tell time correctly. They challenge physicists in their chalk-covered rooms, and they challenge poets in their metaphors. They bend starlight, but they also bend imagination. In them, we glimpse not only what the universe is made of, but how we might think differently about ourselves, as beings woven into a fabric that can stretch and fold, not rigid points, but gentle curves in a larger whole. So the next time you hear of a black hole, perhaps a new discovery, an image released by a telescope, or a ripple of gravitational waves detected by instruments here on Earth, try to imagine it not as a distant monster, but as a quiet guide, a signpost, a dark yet shining reminder that the cosmos is not finished revealing itself, and that each hidden corner may yet be a map waiting to be unfolded. If black holes are the punctuation marks of the universe's story, then gravity is the ink. It flows through every sentence, holding each line in place, yet it is so quiet that we rarely notice it at all. Most of the time it is simply there, pressing your body against the mattress, keeping the coffee in your cup, coaxing the moon to pull the tides in and out like a slow breath. Gravity has no colour, no sound, no texture you can touch, and yet it is the force that shapes the grandest patterns of the cosmos. It sculpts stars, choreographs galaxies, and whispers instructions to everything with mass, from pebbles in your shoe to the blazing arcs of comets. It is, in every sense, the quiet sculptor of existence. The story of gravity often begins with an apple, or at least with the legend of one. Sir Isaac Newton in the late 17th century is said to have watched a fruit fall from a tree and wondered why it fell down rather than sideways. The story has been embroidered over the years, but at its heart it captures something simple. Newton looked at a common event and asked an uncommon question. Out of that question came the idea that every object in the universe pulls on every other object. You, me, the trees outside, even the apple itself. We're all tugging faintly on one another, though Earth, being large and insistent, wins our attention. Newton's laws worked with astonishing precision, explaining the orbits of planets, the paths of cannonballs, even predicting the return of Halley's Comet. His vision of gravity as an invisible force that reached across space endured for centuries, guiding sailors, astronomers, and engineers alike. And then came Einstein. Where Newton had imagined forces, Einstein imagined shapes. In 1915, with his theory of general relativity, he suggested that gravity was not a tug transmitted across distance, but a bending of the very fabric of space and time. Imagine the universe as a vast sheet of fabric stretched taut. Place a bowling ball on it, and the fabric dips. Roll a marble nearby, and it curves inward, not because the ball has tugged on it, but because the marble is following the bend in the sheet. In Einstein's universe, Earth orbits the Sun, not because it is pulled by some invisible string, but because the Sun has curved the stage on which Earth moves, and Earth simply follows the straightest possible path along that curve. This was more than a clever metaphor. It explained phenomena that Newton's framework could not. Light, for instance, has no mass, so how could gravity affect it? Yet during a solar eclipse in 1919, astronomers confirmed that starlight passing near the Sun was bent, deflected by the curved space-time around it, exactly as Einstein had predicted. Overnight, relativity moved from an elegant theory to a proven description of reality. The fabric of space-time was real, and gravity was its sculpting hand. The beauty of Einstein's picture is that it connects the ordinary to the extraordinary. When you toss a ball to a friend, it follows an arc, landing gently in their hands. That same principle, extended, explains why planets trace ellipses around the Sun, why galaxies whirl in vast spirals and why a star collapsing under its own weight can sink into a black hole. The everyday and the cosmic are not separate worlds, but points on the same curve. The apple falling to Earth and the stars bending around black holes are gestures in the same quiet dance. And yet gravity is peculiar in ways that invite reflection. It is by far the weakest of the fundamental forces, so weak that a simple magnet on your refrigerator can lift a paperclip against the pull of the entire Earth. And still, gravity dominates the universe on large scales, because unlike other forces, it has no opposite. There is no negative mass to cancel positive mass, no way to shield yourself from its presence. It accumulates, builds, and stretches across light years, becoming the architect of galaxies. Its weakness is overcome by its persistence. Gentle but endless, it wins in the long run. Perhaps you can feel something of this in your own life. A whisper repeated often enough can be more persuasive than a shout. A habit, barely noticed at first, can shape years if left undisturbed. Gravity works the same way, subtle in the moment, monumental over time. Every orbit, every tide, every fall of rain is a stroke of its chisel. And black holes? They're simply where gravity's arc grows most dramatic. Imagine clay pressed and pressed again, compacted beyond measure until no space remains unshaped. That is what a black hole is, the extreme sculpture of gravity, where space-time itself has been carved into a pit so deep that even light cannot climb free. To understand gravity fully is to understand black holes, and to understand black holes is to glimpse gravity at its most uncompromising. We can trace its influence not only in equations, but in the shapes we see with our own eyes. Saturn's rings, delicate as lace, are sculpted by gravity tugging on particles of ice and dust. The spiral arms of galaxies unfurl like seashells because gravity guides the stars into those curves. Even the grand filaments of the cosmic web, the vast scaffolding of galaxy clusters, are drawn by gravity's hand. And always, at the densest nodes of this web, black holes sit quietly, anchoring the structures around them. To think of gravity as the quiet sculptor is to notice its paradox. It shapes without being seen, it rules without raising its voice. You cannot block it, nor can you escape it. You can only acknowledge its embrace, whether in the gentle pull of Earth holding you as you drift towards sleep, or in the vast collapse of a star folding into darkness. So tonight, as you lie there, perhaps feeling the weight of your body pressed into the bed, take a moment to imagine that same invisible hand stretching outward. The same pull that holds you here holds the moon in orbit, guides comets along their paths, and shapes black holes in the deep. It is all one gesture, one soft sculpting, carried out across the universe. And if you close your eyes, you may almost feel it. The patient chisel of gravity, etching the contours of time and space, one quiet stroke at a time. If gravity sculpts the paths of stars and planets, then it also sculpts something less visible, but far more intimate, the flow of time itself. We often treat time as steady, a clock beating away in the background like the tick of a metronome. But in truth, time is not uniform. It stretches and shrinks depending on where you are and how strongly gravity holds you. Near a black hole, this effect becomes astonishing, as though the very fabric of moments has been pulled and kneaded like soft dough. Time bends like taffy, and in its stretch we glimpse one of the strangest truths of the universe. Imagine placing two clocks side by side on a table, identical in every way, ticking together like twins. Now take one clock and lift it to the top of a tall building, leaving the other at the ground floor. If you compare them after a day has passed, you'll find, after accounting for every careful detail, that the clock upstairs has ticked slightly faster. The one closer to Earth's mass has ticked more slowly. The difference is minuscule, but it is real, and it has been measured many times. You might think of it as if gravity were thickening the syrup through which time flows, making each second stretch just a little longer the deeper you sit in its pool. This is not only an experiment for physicists in laboratories, it is part of your daily life, woven into the systems we rely on. The GPS satellites orbiting Earth experience weaker gravity up there than you do down here. As a result, their clocks tick slightly faster. Engineers must account for this difference, adding corrections so that when your phone tells you where to turn, it doesn't mislead you by miles. Without Einstein's insights into the elasticity of time, your morning commute would quickly descend into a comedy of errors, each car guided by clocks that disagreed. Now, stretch that thought experiment into the cosmos. If time slows near Earth's gravity, imagine how much more dramatically it bends near a black hole. Picture an astronaut hovering just outside the event horizon, carefully balancing with rocket thrust to avoid being pulled in. For them, minutes might pass. To a distant observer, those minutes could appear as hours, days, even centuries. The astronaut's voice, if carried outward, would sound lower and slower, stretched thin like notes dragged across a violin string. Eventually, the signals would fade altogether, red-shifted into silence. The astronaut would seem to hang forever on the edge, suspended in an eternal pause, and yet, from the astronaut's own perspective, their time feels normal. Their heart beats steadily, their thoughts march on, their body ages in its usual rhythm. They would glance at their wristwatch and see nothing strange. For them, the fall across the event horizon is seamless. The paradox lies only in the comparison, the clash of perspectives. It is the same kind of clash you experience when you look back on childhood. Those long summer days that seemed endless when you were 7 feel impossibly short in memory now. The time was the same, but your perspective stretched or compressed it. The cosmos takes this familiar trick and raises it to extremes. Perhaps the best way to picture it is through light. Imagine shining a flashlight up from the surface of a planet. Each photon must climb against gravity, and in doing so, its frequency shifts, its colour reddens. The same thing happens with time itself. Clocks deeper in gravity's well tick more slowly. Their light reddens. The difference is so slight between your feet and your head that it takes precision instruments to measure. But near a black hole, the difference becomes cosmic. What feels like seconds inside can become centuries outside. The fabric of time stretches so dramatically that it challenges our very notion of simultaneity, of what it means for two events to happen at the same time. This idea has fascinated not only physicists but storytellers. You may remember films where astronauts visiting a planet near a black hole return to their ship, only to find decades have passed for their companions. Though dramatized, the core is scientifically sound. Time dilation is not fiction. It is part of the universe's quiet rule book, tested by atomic clocks, verified in the orbits of satellites, and made extreme by the edges of black holes. It can be tempting to think of this as unsettling, even frightening, the idea that time itself is not steady, that your seconds and mine may not agree. But there is also a gentleness to it. Time is not brittle glass that shatters when pressed. It is soft, pliable, able to stretch to accommodate the universe's curves. Like dough rising in the warmth of an oven, it swells and reshapes itself gracefully. This pliability is what makes our universe possible. Without it, gravity could not bend light. Galaxies could not form. Black holes could not whisper their secrets. And if you look closely, you will notice echoes of this pliability in everyday life. Waiting in a doctor's office makes time feel sluggish. Sitting with a dear friend makes hours feel like minutes. Though not governed by relativity, these human perceptions are reminders that time is never quite as simple as we imagine. It bends to context, whether cosmic or personal. So the next time you glance at a clock, remember that it is not keeping universal time. It is keeping your time at your place in Earth's gravity. Someone high in orbit ticks a little differently. Someone near a black hole would tick differently still. We're all carrying personal clocks, each whispering a rhythm tuned to its own position in the cosmos. Near black holes, those whispers diverge into symphonies almost beyond recognition. Seconds and centuries become entangled, and the idea of now stretches until it almost loses meaning. But perhaps that is less a loss than an invitation, to see time not as rigid but as flexible, not as a ruler but as a fabric, woven and reshaped by the quiet sculptor we call gravity. And in that recognition lies something calming. If time itself can stretch, then so can we. If the cosmos can accept many rhythms, perhaps we too can be gentle with our own pace, allowing our moments to unfold in their own way without hurry. So far, we've lingered on the edge of black holes, circling their horizons like curious birds hovering above a canyon. We've watched time stretch and signals fade, and we've imagined what it might feel like to drift toward that invisible boundary. But eventually, curiosity whispers a question that feels inevitable. What lies inside? What happens once something passes that curtain and slips into the region no light can escape? The answer, as it turns out, is both simple and profoundly unsettling. We do not know. The event horizon marks more than just a boundary for matter and light. It is also a boundary for knowledge. From the outside, no signal, no photon, no particle can emerge once it has crossed that line. Whatever story continues beyond the horizon, it cannot be told to those of us watching from a distance. It is as though the universe itself has drawn a curtain across the stage, allowing us to watch the actors step toward it, but never to witness the scene that follows. We can speculate, we can calculate, but direct observation is forbidden. What we do know comes from the equations of general relativity. When Einstein's field equations are applied to a collapsing star, the math insists that all the mass sinks to a single point of infinite density, a singularity. At this point, space and time as we know them no longer behave. Distances shrink to zero, time intervals collapse, and the curvature of space-time becomes infinite. It is as though the universe has asked its equations a question they cannot answer, and the equations respond by breaking. To physicists, infinities are rarely comforting. They signal not clarity but incompleteness, a reminder that the theory is being stretched beyond its limits. General relativity is superb at describing planets and stars and galaxies. It is less reliable at describing the quantum jitter of particles and fields. A singularity, then, is likely not a literal point of infinite density, but rather a sign that our current theories are incomplete. A placeholder, a blank space on the map marked with the old cartographer's warning, "Here be dragons." And yet, though we cannot see inside, we can imagine. Suppose you were an astronaut who has resigned yourself to falling past the horizon. At first, as you cross, you would feel nothing unusual. The horizon is not a wall or a surface. It has no texture, no sound, no glow. But once inside, the paths available to you shrink rapidly. Space no longer offers ways outward. All lines, no matter which way you turn, lead further in. You could aim your rockets upward, sideways, diagonally. It makes no difference. The geometry itself funnels you toward the singularity. In this sense, falling inward is not so much being dragged as being guided, as though the very stage beneath your feet has tilted, and all you can do is follow. Here is where the imagination trembles. Approaching the singularity, the gravitational forces grow extreme. The difference in pull between your head and your feet, what scientists call tidal forces, becomes immense. In small black holes, this would tear you apart long before you reach the center, stretching your body in a process poetically nicknamed spaghettification. In larger, supermassive black holes, the tidal gradient at the horizon is gentler, meaning you could cross without immediate harm. but deeper in, the forces become overwhelming regardless. Eventually you would be pulled into the singularity itself, your matter and your information compressed into the unknowable. From our perspective outside though, your story has already ended. We never see you cross, never watch the final plunge. To us, you're frozen at the edge, fading slowly from view, your signals red-shifted into silence. The contradiction is not in what happens, but in how perspective shapes the tale. Inside, you fall on. Outside, you fade away. Both stories are true, yet neither is complete. The horizon enforces that gap. In a sense, black holes remind us of the limits of knowledge. We live in an age that often celebrates discovery, where telescopes and microscopes pry open distant and tiny worlds alike. But black holes hold their core secrets beyond reach. They insist that some truths may remain hidden, not because we lack clever instruments, but because the structure of the universe itself prevents us from knowing. That is not a defeat. It is an invitation to humility. Still, physicists are not content to leave the blank space uncharted. Quantum mechanics whispers that no information should ever be truly lost. Relativity shouts that singularities cannot be avoided. The tension between them drives whole fields of research. Perhaps at the heart of a black hole lies not a point but a bridge, a wormhole to another region of space-time. Perhaps the singularity is softened by quantum gravity, replaced by a dense core where new physics emerges. Perhaps black holes are not endpoints but transitions, places where our current maps end and deeper ones must begin. For us tonight, though, we need not resolve these debates. It is enough to acknowledge the mystery, to imagine the horizon not as a border of terror, but as a line of quiet dignity, where knowledge bows and admits its limit. In your own life, you may know moments like this, times when you cannot know what lies ahead, when the future is concealed, when all you can do is step forward and trust. A black hole is the cosmos's version of that. A horizon you cannot peer beyond, a center you cannot describe, a silence that cannot be broken. And yet, there is a strange comfort in this. The universe is vast and old and filled with light, but it has kept some secrets for itself. Not everything must be revealed at once. Not every answer must be handed over. Sometimes, the presence of a mystery is as nourishing as the solving of it. Black holes, with their hidden interiors, remind us that wonder thrives in the unknown as much as in the known. So as you rest tonight, imagine the horizon not as a fearful border, but as a quiet curtain. Behind it, the play continues, unseen. One day, perhaps, our equations will change, our understanding will deepen, and we will write more of the script. For now, it is enough to watch the curtain sway in the cosmic wind, and know that something profound unfolds beyond, in the place we cannot see. In 1974, a young physicist named Stephen Hawking shook the foundations of science, with an idea so unexpected that even he resisted it at first. Until then, black holes had been understood as the ultimate prisons, regions that swallowed everything, even light, and gave nothing back. They were thought to be silent, dark, and final. But Hawking's calculations whispered something different, something almost mischievous. Black holes were not perfectly black. They glowed. Not with a blazing fire like stars, but with a faint whisper of warmth, like embers that refuse to die. To appreciate the audacity of this discovery, you have to imagine the context. At the time, physicists were already juggling the strange worlds of relativity and quantum mechanics. Relativity described black holes as inescapable pits carved in space-time, while quantum mechanics insisted that empty space was never truly empty, but fizzing with fleeting particles popping in and out of existence. Hawking decided to bring the two worlds together to see what quantum rules might say about the edge of a black hole. The answer was startling. Near the event horizon, quantum fluctuations constantly create pairs of particles and antiparticles. Normally, these pairs annihilate one another almost instantly, disappearing back into the vacuum. But at the edge of a black hole, something unusual can happen. One particle may fall inside while the other escapes outward. To an outside observer, it looks as though the black hole has emitted a particle, a tiny packet of energy. Multiply this process across time and across countless pairs, and you realize the black hole is leaking ever so slightly, like a coal releasing its last wisps of heat. The effect is called Hawking radiation, and though it is unimaginably faint, it carries profound meaning. It means black holes are not eternal. They can, given enough time, evaporate. The largest black holes in the universe will take trillions upon trillions of years to vanish, far longer than the current age of the cosmos. But the principle stands. Even the darkest objects must eventually fade. The cosmos, it seems, keeps no absolute secrets. Think of it this way. Imagine standing by a campfire late at night. Long after the flames have died, the logs still glow faintly, releasing their warmth into the air. If you place your hand close, you feel the heat, not enough to burn, but enough to remind you that fire once lived here. Black holes, in Hawking's picture, are like those logs. They may appear cold and silent, but deep in their fabric they release whispers of warmth, testimony to a cosmic fire still smouldering. It is worth pausing here to notice how remarkable this is. For centuries, black holes were imagined as ends, final, silent abysses. Hawking's insight turned them into participants in the ongoing thermodynamics of the universe. They became actors in the same drama that governs your cup of tea cooling on the counter, or the ice cube melting slowly in a glass. The laws of heat, entropy, and energy apply even at the event horizon. The same simple principles that make your morning coffee grow cold dictate the destiny of black holes. Of course, this radiation is so faint that it has never been directly observed. To detect it would require measuring signals far weaker than the faintest starlight, drowned out by the glow of the universe itself. And yet, the mathematics is so compelling, so consistent with the rules of quantum mechanics, that most physicists accept Hawking's result as one of the great revelations of the 20th century. It is a discovery not of telescopes but of chalkboards, born from careful thought experiments and stubborn equations. What does it mean, though, beyond the equations? It means the universe is not content to let any object remain forever. Stars burn out, galaxies drift apart, and even black holes, the most tenacious structures we know, must one day yield their energy back to the void. The cosmos, in its quiet way, ensures that nothing can cling to existence eternally. Everything recycles, everything fades, everything gives back. You might feel a tug of melancholy in that thought, the idea that even black holes, those titans of gravity, cannot last. But there is also something deeply harmonious in it. The rules that govern the smallest particles also govern the largest giants. The universe plays fair, applying its laws without exception, and in that fairness there is beauty. Hawking himself often described his discovery with a hint of dry humour. Here was a man who had devoted his career to exploring black holes, only to find that they might not be quite as black, or as eternal, as he had once believed. But that was the nature of his genius, to follow the equations wherever they led, even if they undermined the very mysteries that had first inspired him. Imagine for a moment a cosmic clock, ticking away across unimaginable spans of time. Galaxies collide and drift apart, stars ignite and extinguish, planets form, thrive, and vanish. And in the background, black holes glow ever so faintly, shrinking slowly as they release their last warmth. It is a timeline so long that human imagination strains to grasp it. And yet, Hawking radiation gives us a glimpse of it, a vision of the universe not as static, but as an endless unfolding, where even the darkest shadows cannot last forever. So the next time you see a dying fire, coals glowing softly in the dark, think of Hawking's insight. Black holes are not silent tombs, but smouldering embers. They whisper their presence in the faintest glow, reminding us that even in the deepest darkness, the laws of nature keep working, quietly, persistently, without pause. That whisper, once revealed, changed the way we see the universe. It turned black holes from eternal mysteries into temporary chapters, glowing softly as they wait to be turned. If Hawking radiation revealed that black holes were not silent, it also opened a door to a riddle that has haunted physics ever since. The riddle is simple to state but dizzying to solve. What happens to information that falls into a black hole? When you drop a letter into a mailbox, you assume it will be delivered somewhere, or at least stored in a warehouse if it cannot be. But what if there were a mailbox that simply burned every letter it received, leaving no trace behind? That, in essence, was Hawking's suggestion. To see why this was so shocking, we must pause for a moment and consider what physicists mean by information. In ordinary life, information is words on a page, songs on a radio, pictures on a phone. In physics, information is broader. It is the complete description of a system, the position of every atom, the spin of every particle, the state of every field. It is the story of matter written in the tiniest details. And one of the bedrock principles of quantum mechanics is that information is never lost. It can be scrambled, hidden, transformed, but not annihilated. Think of burning a book. To your eyes, it may look as though the story is gone, but at the microscopic level, the ink and paper have turned into smoke, ash, and heat. The molecules still carry the traces of what was once there. In principle, if you could track every particle, you could reconstruct the original story, page by page. This is the stubborn law of quantum physics. The universe is a diligent archivist. It never allows information to vanish completely. And yet, according to Hawking's early calculations, black holes seem to do exactly that. Matter falls in, carrying with it the delicate arrangements of particles and fields that make up its identity. Over time, the black hole radiates away its mass as Hawking radiation. But that radiation, as Hawking described it, is purely thermal, like the featureless glow of a hot stove. It contains no trace of the original details. A star, a library, a spaceship, all would produce the same bland output once swallowed. When the black hole finally evaporates, nothing remains. The information has been destroyed. This conclusion horrified many physicists. If true, it would mean the universe breaks its own rules. The careful conservation of information, observed in every experiment, would fail at the event horizon. Reality would be inconsistent. For some, this was unacceptable. For others, it was thrilling. A sign that our current theories were incomplete, that some deeper law waited to be discovered. The paradox was soon named the black hole information paradox, and it has remained one of the most stubborn puzzles in modern physics. On one side stood the principles of quantum mechanics, demanding that information cannot be lost. On the other stood the calculations of relativity and Hawking radiation, suggesting that black holes erase information permanently. It was as though two languages of nature, each coherent on its own, produced a contradiction when asked to describe the same scene. The paradox quickly captured the imagination not only of scientists but of the wider public. Perhaps because it resonates with something familiar, the fear of losing stories. When we forget a memory, when a library burns, when a language dies, we sense something irretrievable has been taken. The idea that the universe itself might operate the same way, erasing stories in black holes, felt both tragic and deeply human. And yet, we should be careful. The paradox is not about human memory or cultural stories. It is about the laws of physics. Still, the metaphors help. A black hole, in Hawking's early picture, was like a shredder that reduced every book to confetti and then threw the confetti into the fire, leaving only heat. To the laws of quantum mechanics, that outcome was intolerable. It would be as though the grand library of the cosmos had decided to discard entire volumes without a trace. Physicists debated fiercely. Some sided with Hawking, believing perhaps the universe did destroy information, that quantum mechanics would have to bend. Others believed the radiation must contain subtle patterns, hidden in the noise carrying the story outward. Still others imagined exotic possibilities. That information might leak into parallel universes, or be preserved on the horizon itself like writing on a cosmic ledger. In everyday life, we might shrug at such abstractions. But to scientists, the stakes were enormous. If information could be lost, then predictability itself would collapse. The ability to trace cause and effect would be broken. The very idea that physics describes a lawful universe would be shaken. It is no exaggeration to say that the information paradox struck at the heart of science. And yet, there is a quiet poetry in this too. The paradox reminds us that even in an age of space telescopes and quantum computers, the universe keeps some riddles intact. Black holes are not only physical objects but also philosophical mirrors. They reflect back our assumptions about knowledge, memory and permanence. Do stories ever truly vanish? Or are they always written somewhere, even if we cannot read them? As you rest tonight, imagine tossing a book into a fire. To your eyes, the story vanishes. But in truth, the smoke carries patterns of ink molecules. The ash carries carbon from the pages. The heat carries vibrations that once belonged to letters. The story is scrambled, unreadable, but not destroyed. Hawking's black holes seem to suggest otherwise, that there are places in the universe where stories end without trace. Whether that is true remains the puzzle, and it is a puzzle that continues to draw physicists like moths to a flame. For decades after Hawking first announced that information might be destroyed in black holes, the scientific community wrestled with his claim like a knot too tight to untangle. Arguments flowed back and forth, conferences grew heated, and papers stacked upon papers. Some physicists defended Hawking's position, convinced that the universe might indeed permit stories to vanish completely. Others resisted with equal passion, unwilling to accept that the cosmos would betray such a fundamental rule. The debate stretched on for years, like two chess players circling the same board, moving pieces slowly but with growing intensity, and then slowly, new ideas began to soften the impasse. One of the most compelling was the notion that perhaps information is not lost inside the black hole at all, but somehow encoded on its surface. This idea grew into what is now called the holographic principle, and it offered a way to reconcile quantum mechanics with relativity without sacrificing the conservation of information. The holographic principle is one of those concepts that sounds almost mystical at first, yet it arises from rigorous mathematics and careful reasoning. At its heart is a simple but astonishing claim. Everything that happens inside a region of space might be fully described by information stored on its boundary. In other words, the universe may be like a hologram, where a two-dimensional surface encodes a three-dimensional volume. For black holes, this means that all the information about what falls in, the details of every particle, every arrangement, might not vanish into the singularity but instead remain imprinted on the event horizon itself. Think of it like a balloon. Before you inflate it, you could write tiny notes, diagrams, or codes on its surface. As the balloon expands, those markings stretch, but they are still there, preserving the details. The inside of the balloon may be empty, but the surface carries the record. In the same way, a black hole's event horizon could act as a cosmic ledger, storing the stories of everything that has crossed it. This was a radical shift, but it resonated deeply. It allowed physicists to preserve the cherished principle that information is never destroyed, while still respecting the strange properties of black holes. And it did more than that. It hinted that perhaps this was not only a property of black holes, but of the universe itself. Perhaps our entire cosmos is holographic, with its true information content encoded not in the depths, but at the edges. Of course, this does not mean that our world is an illusion, or that you're a flat image on some cosmic wall. It means that the mathematics describing reality may work in surprising ways, and that boundaries may be more fundamental than interiors. For many scientists, this principle felt less like a desperate patch, and more like a window into deeper truths. Stephen Hawking himself eventually softened his stance. In his later years, he conceded that information might not be lost after all, though the exact mechanism remained elusive. For some, this was a relief, a reassurance that the laws of physics remained intact. For others, it was a reminder that even the most brilliant minds must sometimes yield to the persistence of evidence and the creativity of colleagues. There is something hopeful in this story, beyond the technical details. At first, the paradox looked like a dead end, a wall blocking our understanding. But by sitting with it, by refusing to look away, physicists found a new path. That path may one day lead to a deeper unification of quantum mechanics and relativity. Black holes, once thought of as cosmic destroyers, became guides instead, pointing us toward the possibility that the universe is stranger, subtler, and more coherent than we had dared to imagine. And if you step back for a moment, you might notice how this echoes in your own life. We all face paradoxes, moments that seem contradictory, problems that refuse to yield. At first they feel hopeless, as though they have trapped us. But sometimes, by dwelling with them, by listening carefully, they reveal new perspectives. A paradox is not always a wall. It can be a doorway disguised. Black holes remind us of this lesson on a cosmic scale. The holographic principle also carries a kind of poetic comfort. Imagine that every event in your life, every thought, every gesture, every kindness, is not lost but inscribed somehow on the boundary of reality itself. You're not erased, even if time scatters the details. The universe keeps its records, written in ways we cannot yet read. Whether literal or metaphorical, the idea resonates. Nothing is ever completely gone. So when we think of black holes now, we do not see them only as places where stories end. We see them as places where stories are transformed, compressed, and written anew. Their horizons are not blank curtains, but surfaces covered with invisible ink, waiting for us to learn how to read it. And in that sense, the information paradox has given us more than a puzzle. It has given us a vision of the cosmos as a place where information, like memory, is never discarded, only reshaped. Black holes are no longer shredders of books, but libraries with locked doors, their volumes stacked neatly on the walls. We may not yet know the key, but the books are still there. From paradox to hope, that is the arc of this story. What began as a terrifying possibility, the annihilation of information, has evolved into an invitation to think differently about space, time, and the nature of reality itself. And as we move onward in this journey, we will see that black holes are not monsters lurking in the dark, but teachers, whispering lessons about order, entropy, and the hidden architecture of the cosmos. When you think of entropy, you might picture the slow unraveling of order in everyday life, the laundry piling up, the coffee growing cold, the bread going stale on the counter. Entropy is the tendency of systems to become more disordered over time, to spread out energy, to shuffle neat arrangements into messier ones. It is one of the most universal rules of the universe, a rule so dependable that some call it the arrow of time itself. Cups break, but shards do not leap back into a cup. Smoke disperses, but it does not gather back into the logs it once was. Entropy always increases. Now, here is the surprise. In the early 1970s, a young physicist named Jacob Bekenstein began wondering what happens when entropy meets a black hole. Suppose you take a hot cup of tea. steam swirling, molecules buzzing with energy, and toss it into a black hole. From the outside, all you see is the cup cross the event horizon and disappear. Its heat, its molecular dance, its information, all gone. At first glance, it looks as though entropy has been erased, which violates the rule. And yet, the laws of physics leave little room for exceptions. If entropy always increases, it must increase here too. Bekenstein proposed a daring idea. Perhaps black holes themselves have entropy, an internal measure of disorder that grows as they consume more matter and energy. And perhaps this entropy is not proportional to their volume, as you might expect, but to the area of their surface, the event horizon. In other words, the size of the black hole's hidden library is measured not by how much space it encloses, but by the size of its boundary. This was a shocking claim. In ordinary life, the amount of information you can store usually grows with volume. A bigger hard drive holds more data. A bigger jar holds more marbles. Why should a black hole's information be tied to its surface instead? And yet, Hawking's later calculations on black hole radiation confirmed that Bekenstein was right. The entropy of a black hole is proportional to the area of its horizon, not its interior volume. To make sense of this, imagine a messy room. Clothes scattered on the floor, books piled at odd angles, mugs on the desk, crumbs in the carpet. Even if you close the door and lock it, the mess still exists inside. If a friend asked, "Is the room messy?" you could answer yes, even without seeing it. Entropy counts even when it's hidden. Black holes, Bekenstein suggested, follow a similar logic. The mess of information inside is accounted for, but instead of being measured by the volume of the room, it is measured by the size of the door itself. This strange link between area and information planted the seed for the holographic principle we touched on earlier. If the information content of a black hole grows with its surface, maybe the universe itself works that way. Perhaps the true ledger of reality is written on surfaces, not in interiors. The connection between entropy and black holes also led to what physicists now call the 4 laws of black hole mechanics, which mirror the 4 laws of thermodynamics you might learn in school. Black holes have temperature, entropy, and energy, and they obey rules about how those quantities change. Suddenly, these dark enigmas were no longer exceptions. They were part of the same thermodynamic family that governs ice melting in a glass and engines humming on a road trip. The cosmos had drawn no line between the everyday and the extreme. There is something delightful about this. It means the same rule that explains why your toast always lands butter side down also explains the destiny of black holes. Entropy is a unifying thread, weaving together kitchens and galaxies, laundry baskets and event horizons. But there is also a deeper comfort in it. Entropy, for all its association with disorder, is not the enemy of order. It is the measure of possibility. The more entropy a system has, the more ways its pieces can be arranged. A deck of cards neatly stacked has low entropy. Shuffle it, and entropy rises, because there are so many more possible shuffles than perfect orders. Black holes, then, are not graveyards but repositories of possibility, places where information is not destroyed but hidden, waiting on the surface in ways we cannot yet decode. Imagine pressing your hand into wet sand at the beach. You leave a print, a record of your presence. The tide may come, the wind may blow, but for a while the surface keeps the story of your touch. Black holes may work in the same way, imprinting the details of everything that falls in on their horizons. To us it looks blank. To the laws of physics, the story is still there. So the next time you sigh at the mess in your room, or watch steam rise from a cup of tea, consider that entropy is not just disorder, but a profound connection to the universe's deepest laws. It stretches from your desk to the stars, from a locked door to a black hole. And at the edge of those cosmic abysses, entropy continues its work, counting, recording, insisting that nothing is erased, only transformed. When you think of temperature, you probably imagine things you can touch, the warmth of sunlight on your skin, the chill of a winter morning when you first step outside, the steam curling from a pot of soup. Temperature feels like a measure of comfort, a number that tells you whether to reach for a sweater or a glass of ice water. In physics, though, temperature is more than sensation. It is a measure of how much energy is jostling around inside a system, how restless its particles are, how much motion stirs beneath the surface. And by that measure, even black holes, those silent, lightless giants, must have a temperature of their own. The idea is strange at first. How can something that swallows all light, that allows nothing to escape, possibly be said to glow? For a long time, scientists believed black holes were perfect absorbers, objects that could take in everything yet emit nothing. But Hawking's insight in the 1970s changed that forever. By applying quantum mechanics to the horizon, he found that black holes radiate faintly. This radiation is unimaginably weak for large black holes, but it is enough to assign them a temperature. They are not infinitely cold, but instead possess a subtle warmth, a kind of whispering heat that links them to the same thermodynamic rules governing stars, oceans, and teapots. To appreciate how counterintuitive this is, imagine sitting by a campfire. As the flames die down, the logs glow softly, releasing the last of their stored energy. The air above shimmers with heat. Now, take away the light entirely. No flames, no embers, just darkness. And yet, suppose you place your hands near this dark log and feel warmth radiating out. That is what Hawking's discovery suggests. Even in the deepest darkness, there can be a trace of temperature, a faint breath of heat whispering into space. The temperature of a black hole depends on its size. Paradoxically, the bigger the black hole, the colder it is. A stellar mass black hole, a few times heavier than the Sun, would have a temperature of billionths of a degree above absolute zero, utterly undetectable. A supermassive black hole, like the one at the centre of the Milky Way, is even colder than the faint afterglow of the Big Bang that fills the universe. These giants are not only dark, but drowned in cosmic background radiation, making their own glow invisible. By contrast, tiny hypothetical black holes, if they exist, would be hotter, radiating more intensely, perhaps even enough to shine in bursts before evaporating entirely. There is a quiet elegance in this relationship. The largest, most fearsome black holes are also the coldest and slowest to fade. The smallest, fragile ones burn away quickly. It mirrors the rhythm of many things in life. The biggest fires burn longest, but cool slowly. Small sparks flare brightly and vanish. A pot of soup stays warm for hours, while a spoonful cools in minutes. Nature seems to delight in these inversions, tying size to tempo in ways that surprise us. What matters most, though, is that the existence of a temperature brings black holes firmly into the domain of thermodynamics. They are not strange exceptions outside the rules, but participants in the same universal laws that govern every system. A black hole has entropy, energy, and temperature. It can radiate, cool, and over immense spans of time evaporate. They are not eternal abysses, but temporary states in the ongoing flow of the cosmos. This realization reshaped how physicists saw black holes. Instead of monsters devouring everything, they became part of the cosmic cycle, releasing energy back into space. Their eventual evaporation, though it lies in a future so remote it feels almost mythical, is still part of the universe's long-term accounting. No energy is locked away forever. No shadow is absolute. From a more poetic perspective, there is comfort in this. Imagine a cold night in the countryside, the sky clear and filled with stars. Around you, the air is silent, still. Yet, even here, faint warmth radiates from every body, from the ground beneath you, from the breath of the earth itself. Black holes too radiate faintly and persistently, reminding us that nothing in the universe is beyond the reach of thermodynamic law. Even darkness has a temperature, and perhaps there is a lesson here for us too. We sometimes think of the darkest moments of life as absolute, as though they contain nothing of value, nothing to give. But even in those moments, something radiates, a trace of warmth, a fragment of meaning, an ember that glows quietly in the background. Black holes embody this paradox on the grandest scale. They are as dark as anything we know, yet they shine in the faintest way possible. So the next time you sip from a cup of tea and feel it slowly cooling, or notice the last heat fading from a pan after cooking, think of a black hole. Somewhere perhaps millions of light years away, one of these giants is also cooling, radiating faintly into space following the same laws. It may take longer than the lifetime of galaxies, but eventually it too will fade. In this shared process from your kitchen to the cosmos, we glimpse a continuity that binds everything together. Black holes are not monsters beyond the reach of order. They are subjects of the same rules that govern steam, soup, and sunlight. Their temperature may be small, their radiation faint, but those whispers matter. They tell us that the universe plays no favourites. Darkness too must obey the laws of heat. Time feels so basic, so obvious, that questioning it almost sounds absurd. You wake in the morning, the clock reads 7, you drink your coffee, minutes pass, the sun arcs, the afternoon fades, the evening arrives. Life seems to unfold as a steady current, carrying you forward from past to present to future. Surely we think this current must be one of the universe's most fundamental features, something that exists independently of us. And yet some physicists, Carlo Rovelli, among them, suggest that time may not exist at the deepest level of reality. What we experience as time might be less like a river and more like an illusion created by the way we move through the world. Rovelli's argument is not that time is fake in the sense of being imaginary or useless. It is real enough for daily life, for clocks, for seasons and calendars. But at the deepest scales, when we look into the equations that describe quantum gravity, time does not appear as a fundamental ingredient. It seems to emerge instead, like a melody emerging when individual notes are played in sequence. Without the notes, there is no melody. Without the events and changes, there may be no time. A helpful way to picture this is to imagine a roll of film. Each frame is a still picture, frozen and silent. Alone, a single frame conveys a moment, but nothing more. Only when you project them in sequence at the right speed does the illusion of motion arise. The characters walk, the leaves flutter, the story unfolds. Motion is not in the frames, it is in the way they are played together. Time, Rovelli suggests, may be like this. The universe contains states, arrangements, snapshots of being. What we call time is the sense of flow we get when those states are stitched together, when one follows another in our perception. This is not just philosophy dressed in scientific clothing. In the equations of general relativity, time is already slippery. Clocks in different places do not agree. There is no universal tick, no master clock that dictates the same moment everywhere. And in quantum mechanics, the basic laws are timeless. They describe probabilities, relationships and symmetries, but not an arrow pointing forward. Time only emerges when we ask questions about change, about how one state becomes another. Black holes provide a particularly sharp clue to this mystery. Near the event horizon, time slows dramatically compared to the outside. Inside, the very concept of before and after becomes tangled. A falling observer experiences one story. A distant observer experiences another. Which is the real time? Both are valid, but they do not align. The contradiction suggests that time is not as fundamental as we assume, but something woven from relationships, from perspective, from context. It is not a stage on which the universe acts, it is part of the play itself written into the script. If this feels unsettling, you are not alone. Humans are wired to experience time as linear, to measure life in birthdays and anniversaries, to imagine the future as a path stretching ahead. To hear that time might not exist fundamentally is like being told that colour is not in the world but in your brain. It does not change the reality of what you see, but it shifts your understanding of where that reality comes from. Perhaps a gentler way to think of it is this: time is a story. It is the way we stitch events together into a sequence that makes sense to us. A day is 24 hours because Earth spins once. A year is 365 days because Earth orbits the Sun. But in a universe without spinning planets or orbiting stars, would those hours and years mean anything? Without change, time loses its meaning. Without events, clocks have nothing to measure. Even in your own life, you can sense this relativity of time. Recall a day spent waiting anxiously. The hours crawl, each minute stretched. Then recall a day spent absorbed in joy or creativity. The hours fly, leaving you startled that evening has arrived so quickly. The clock on the wall ticks the same, but your experience stretches and compresses. At the cosmic level, perhaps the universe itself treats time this way, not as a rigid metric, but as a flexible story that emerges from motion and memory. Black holes, again, are the extreme. At their horizons, time bends so fiercely that it almost breaks. To one observer, events freeze. To another, they continue. To reconcile this, physicists suspect that time itself is not an independent entity, but a derived one, emerging from deeper quantum interactions. Some researchers even suggest that time is born from entanglement, from the correlations between particles. In this picture, what we call the flow of time is really just the way information knits together across the universe. If so, then time is not fundamental, but it is still precious. Like the melody of a song, it exists because of the arrangement beneath it. Remove the notes, and the melody vanishes. Remove the relationships, and time dissolves. But as long as the music plays, we can enjoy the tune. There is a strange comfort here. If time is emergent, then perhaps the past and future are not lost or unreachable, but simply parts of the greater arrangement, waiting for their place in the sequence. Perhaps your memories and hopes are not drifting into nothingness, but are threads woven into the larger fabric. You move along it like a reader turning pages, but the story as a whole is already written, already present, already part of the universe's deeper order. So tonight, as you listen, imagine the universe not as a ticking clock, but as a film strip unspooled, each frame a snapshot, silent on its own, but together creating the illusion of flow. Black holes, with their bending of moments, hint that the real is not as simple as we thought, that perhaps time is not the foundation but the narrative. And as you breathe slowly, letting your thoughts drift, remember, the story is still unfolding even if the frames exist all at once. Time is our melody, our illusion, our gift. And whether fundamental or not, it is the rhythm in which we live, the music that carries us gently through the night. Imagine holding a small card in your hand, a square filled with a scatter of black and white pixels. To the untrained eye, it looks meaningless, like static on a television screen. But scan it with your phone, and suddenly it reveals a song, a website, a message. That little flat square, only 2 dimensions, hides the instructions for something much larger. This is how QR codes work, and it is also one of the best everyday metaphors for one of the most daring ideas in modern physics, the holographic universe. The holographic principle suggests that everything within a region of space, every atom, every particle, every swirl of energy, might be fully described by information written on its boundary. In other words, the 3-dimensional world we move through could be the expression of a 2-dimensional script written at the edges of reality. Like a hologram on a credit card, which looks like a 3-dimensional image but is encoded in a thin surface, the universe itself may be a projection of deeper information. This idea first emerged from the study of black holes. Remember Bekenstein's insight that a black hole's entropy, its measure of hidden information, grows with the area of its horizon, not its volume. This was strange but compelling. Then, in the 1990s, physicists like Gerard T. Hooft and Leonard Susskind took the thought further. If a black hole's information is stored on its surface, perhaps the same is true of the entire cosmos. The information that defines everything inside might be written not in the depths but at the edges. It is a bold suggestion, and one that takes time to sink in. We are so used to thinking of the world as volumetric, as filled with depth. The air in your room, the space in your lungs, the distance between stars, these feel like interiors. And yet, if the holographic principle is correct, the true accounting of those interiors is kept on the surface that encloses them. The universe keeps its books on the boundary, not inside the pages. To imagine this, think of a snow globe. Inside, there are tiny houses, trees, and glittering flakes drifting down. But suppose all the instructions for that miniature world were inscribed invisibly on the glass surface. From the outside, you might not see them, but they would be there, encoding every detail of the scene within. The holographic universe suggests something similar, that our reality might be a kind of snow globe, with its true description written on the boundaries of space-time. Another way to feel this principle is to think of shadows. You stand on a sidewalk on a bright afternoon, and your shadow stretches across the pavement. The shadow is flat, a two-dimensional outline, yet it encodes something about you, your shape, your height, the way you hold your arms. From that flat projection, someone could reconstruct at least part of the three-dimensional being you are. Now imagine a universe where every detail, not just the outline, is encoded in this way, where the shadow is enough to rebuild the whole. That, in essence, is what holography claims. Why does this matter? Because it may be the bridge between quantum mechanics and relativity, the two great but mismatched theories of physics. Relativity describes space-time as smooth and continuous. Quantum mechanics describes reality as grainy, probabilistic, filled with uncertainty. Reconciling the two has been one of the greatest challenges of modern science. The holographic principle may provide the key, suggesting that the universe's fundamental description is not in the depths but on the surfaces, where the mathematics of quantum fields and relativity can finally meet. And once again, black holes are our guides. Their surfaces, their horizons, are not blank curtains but rich ledgers, storing the information of everything that has fallen in. What we once thought of as endings may instead be libraries, their shelves encoded in the area of the horizon. The universe does not discard its stories, it writes them on the walls. If this sounds abstract, remember that we are already comfortable with similar ideas in daily life. Your brain, for instance, stores your memories in patterns of connections. A smile, a song, a childhood home. They are not stored as little movies, but as encoded patterns that your brain reconstructs. A compact disc stores hours of music in tiny pits etched on a surface. A hard drive holds photographs as magnetic orientations. Again and again, we accept that rich three-dimensional experiences can be stored in thin, two-dimensional patterns. The holographic universe is a cosmic echo of the same principle. There is, too, a kind of poetry in it. If the world is holographic, then the boundaries matter more than we thought. The edges of things, horizons, surfaces, curtains of light, may be where reality is most fully written. We spend much of our lives looking inward, searching for meaning in depths, but perhaps meaning is inscribed all around us, on the boundaries, waiting to be recognized. So as you imagine tonight, picture the universe not as an endless solid, but as a projection, a magnificent hologram woven from patterns on the edges of space-time. Imagine the walls of the cosmos as pages, each encoding a story too vast to see directly. We live inside the projection, walking through the snow globe, listening to the music encoded in a flat disk, never seeing the code itself but living its unfolding melody. It does not diminish the wonder of the world to think of it this way. If anything, it deepens it. The fact that a flat QR code can hold a song, that a thin disk can hold a symphony, that a delicate surface can hold an entire galaxy's worth of information. This is not a reduction, but a revelation. The holographic universe tells us that reality may be stranger, subtler, and more elegant than our senses alone suggest. And so, the next time you scan a code on your phone or watch light glimmer on the surface of a holographic sticker, pause for a moment. Consider that you might be glimpsing a miniature echo of the cosmos itself, a universe written on a surface, projected into a depth, inviting us to see beyond appearances and wonder at the hidden codes of reality. One of the quiet reassurances of daily life is knowing that memories and information can be stored in more than one place. You might save an important document on your computer, then back it up to an external drive, and maybe even email a copy to yourself just in case. The redundancy is comforting. Even if one copy is lost, another remains. The same principle applies to human memory. You might forget the details of a song, but then hear a friend hum the melody, and the memory comes rushing back. Information, it seems, likes to be resilient. In recent years, physicists have begun to suspect that black holes may work in a similar way. Their horizons may act not only as storage, but as storage with redundancy, preserving information in overlapping ways that make it nearly impossible to erase completely. In the language of quantum physics, this is akin to what we call quantum error correction codes, schemes that protect fragile information by spreading it across many degrees of freedom so that no single disturbance can destroy it. To understand why this matters, consider how delicate quantum information normally is. In the quantum world, particles can exist in superpositions, holding multiple possibilities at once, but this state is fragile. A small interaction with the environment can cause the superposition to collapse, the information to scatter. In computing, this fragility is a challenge. Quantum computers must use elaborate error correction techniques to ensure that the information survives long enough to be useful. By encoding data in redundant ways, they can recover the original message even if parts of it are disturbed. Black holes, some physicists argue, may use a similar strategy at a cosmic scale. When matter falls in, its information is not simply erased or hidden. Instead, it is stored across the horizon in a way that is redundant and robust. If you were able to read the horizon's code, you would find the information not in a single neat file, but in a pattern repeated and overlapped so thoroughly that no part of it could be destroyed without the whole becoming inconsistent. An everyday analogy might help. Imagine writing a sentence on a piece of paper, then photocopying it dozens of times and scattering the copies across a room. Even if half the sheets are lost, the sentence can still be reconstructed. Now imagine not only copying, but also embedding the same sentence in puzzles, crosswords and codes, all interlinked. To lose the message completely, you would have to erase every copy, every hint, every echo. That is what redundancy provides. Resilience. Black holes, it seems, may embody this principle naturally, not by design, but by the fundamental laws of physics. This idea, linking quantum error correction to black holes, was championed by researchers like Leonard Susskind and Juan Maldacena. They suggested that the horizon might act like a quantum computer, encoding and protecting information in sheer ways that resemble the strategies engineers are now trying to harness in laboratories. If true, this would mean that far from being destroyers of information, black holes are its most diligent custodians, protecting it against annihilation with cosmic precision. It is striking to think of a black hole, an object we once imagined as pure destruction, as a librarian, a stern librarian perhaps, who locks the books behind an impenetrable door, but a librarian nonetheless. The information is not shredded. It is carefully catalogued in a language we do not yet speak, redundantly inscribed on the horizon. There is something poetic here too. Human memory works in overlapping ways. You might forget the name of a place, but recall its smell, its light, the curve of its streets. The brain does not store experience in a single file, but in layers and echoes across networks of neurons. Even when one pathway fades, another can rekindle the memory. In a sense, your mind performs its own error correction, ensuring that your stories survive in fragments until they can be pieced together again. Black holes, on a vastly larger scale, may perform a similar trick, encoding the universe's stories redundantly across their horizons. And consider the comfort in this. If the holographic principle is right, and if black holes protect information with such care, then perhaps nothing is ever truly lost. Transformed, yes. Scrambled, yes. But not gone. Every star, every planet, every thought that crosses a horizon leaves a trace, preserved redundantly like backups in a cosmic archive. We may never retrieve those details directly, but the laws of physics insist they endure. This brings us back to the broader idea that space and time themselves may be emergent. If black holes encode information redundantly, and if that information is what gives rise to the geometry of space-time, then perhaps the fabric of reality is built upon the same principles of resilience. Just as your computer reconstructs a file from overlapping data, perhaps the universe reconstructs space and time from the overlapping patterns of information written on horizons. For now, this remains a hypothesis, a mathematical picture waiting for confirmation. But it is a deeply suggestive one. It suggests that the same principles guiding engineers in the design of tomorrow's quantum computers are already at work in the darkest corners of the cosmos. The line between technology and nature, between invention and discovery, begins to blur. So tonight, as you drift toward rest, imagine black holes not as Moore-like destroyers, but as immense archives. Picture them as silent librarians, carefully copying every book, every note, every equation, and placing them redundantly on the shelves of the horizon. No fire consumes these pages, no shredder tears them. They are preserved, awaiting a language we have not yet learned to read. In that vision lies a gentle hope that the universe itself is careful with its stories, that memory is woven into its laws, that nothing is discarded without trace. When we speak of black holes, the word that often rises is singularity. It is a daunting term, conjuring images of infinite density, of mathematics spiraling out of control, of a place where the very fabric of space and time collapses to a point with no volume. At the same time, when cosmologists speak of the origin of the universe, the Big Bang, they also use that same word, a singularity. At both the beginning and the end, at the birth of time and at its apparent death inside a black hole, the universe seems to fold upon itself in similar ways. It is tempting to picture singularities as physical objects, as tiny dots you might peer at if only your vision were sharp enough. But in truth, they are less objects and more signals, signals that our current theories are incomplete. A singularity is the moment when Einstein's equations, usually so reliable, yield infinities instead of answers. It is the universe telling us, here, your map ends. Here, you need a new language. And yet, there is a deep symmetry in the fact that singularities appear at both ends of cosmic experience. When the universe was young, just fractions of a second old, all its matter, energy, and space-time were compressed into a state we cannot describe. Out of that compression came expansion, galaxies, stars, planets, and life. At the other extreme, when a massive star collapses into a black hole, or when galaxies feed their central giants, matter is funneled again into a region where density grows without bound, where our equations fail. It is as if the book of the cosmos begins and ends with the same word, singularity. A gentle metaphor may help. Imagine taking a long sheet of paper, writing a story on it from left to right. At the far left, you fold the sheet sharply, pressing all the words into a single crease. At the far right, you do the same, beginnings and endings compressed into points. The rest of the story stretches between them, full of characters and events, but at both ends it is folded into silence. Singularities are like those creases, folds in the fabric, where words no longer separate, where time and space themselves lose individuality. For scientists, this is more than poetic symmetry, it is a clue. If the universe both begins and ends in singularities, perhaps the two are not so different. Perhaps understanding one helps to understand the other. The mathematics of black holes, paradoxical as it seems, may hold lessons about the birth of the cosmos. The extreme conditions inside black holes might mirror the conditions of the Big Bang. By studying them, we may learn not only about endings, but about beginnings. It also raises a haunting question. Are black holes, in some sense, seeds of new universes? Some speculative theories suggest that the collapse inside a black hole might lead not to annihilation, but to a new expansion on the other side, a kind of cosmic rebirth. In this view, every black hole might cradle a baby universe within, hidden from our own but expanding in its own space-time. We cannot know for now, but the symmetry of singularities makes the thought linger. Even if such speculations are beyond proof today, they stir the imagination. You may find yourself wondering, if a singularity marked the beginning of everything we know, then perhaps endings are not endings at all, but transitions to beginnings we cannot yet see. The death of a star, the collapse of a black hole, the singularity at its core, these might be less like final periods and more like commas, pauses before another clause in a longer sentence. In your own life too, you may have felt something of this symmetry. The end of one chapter, though painful, often carries the seed of another beginning. A job lost, a season past, a farewell spoken, each folds into silence for a time, but eventually unfolds into something new. The cosmos seems to share this rhythm, compressing beginnings and endings into singularities, then letting the story stretch again. Physicists often say that singularities are where our theories break down. That phrase may sound like failure, but perhaps it is more like an invitation. The singularity is a crease where our current mathematics is folded too tightly. If we find new equations, new frameworks that merge quantum mechanics with relativity, perhaps the crease will smooth, revealing what truly happens at those extremes. Black holes, then, are laboratories not only of destruction, but of possibility, reminding us that the most profound insights often emerge where understanding falters. So tonight, as you let your thoughts drift, imagine the universe as a great sheet of paper, its story stretching wide. At one end, the Big Bang folds everything into a singular crease. At the other, black holes press matter and time into another fold. Between them lies the story we inhabit, with stars, oceans, and hearts beating quietly in the night. Perhaps the folds are not so different. Perhaps beginnings and endings are two sides of the same gesture, both whispering the same truth, that out of silence stories emerge and into silence they return. The question of beginnings has haunted human thought for as long as there have been stories. Where did everything come from? Was there a moment when the universe began, or has it always existed in some form? Religions, myths, and philosophies have all offered their own answers, weaving creation tales of gods and cosmic eggs, of cycles and eternal returns. Science, too, has stepped into this ancient conversation, and nowhere does the question feel sharper than when we look into the heart of black holes. For black holes, like the universe itself, seem to ask, what happens when time itself runs out? When we trace the history of the cosmos backward with Einstein's equations, we find galaxies moving apart, stars retreating into the past, radiation growing hotter, denser, until finally the math points to a beginning, a singularity some 13.8 billion years ago, the Big Bang. In that instant, the universe itself was compressed into a state we cannot describe, and from that compression, time and space themselves expanded. But what does it mean to say, the universe began? If time is part of the universe, can we even ask what happened before? Before may be a word with no meaning in such a context, like asking what lies north of the North Pole. Black holes bring this question closer to hand. When matter collapses into a singularity, time as we know it ends there too. For the falling observer, their clock continues ticking until the end, but beyond the singularity there is no after. The equations simply stop. It is as though time is a sentence that ends in mid-word, not because the story was finished, but because the language itself ran out. Some physicists suggest that perhaps the universe had no true beginning. Perhaps the Big Bang was not the start of time, but a transition, like water boiling into steam. In this view, there was something before, but it was not time as we know it. It was a different phase of reality, incomprehensible to us but no less real. Black holes hint at this possibility, because they too seem to transform the familiar rules of space and time into something we cannot yet articulate. An everyday metaphor might help. Think of a clock sitting on a shelf with no battery. You can point to the hands, the numbers, the shape of the face, but without the battery, the clock does not tick. It has no before or after, only stillness. When the battery is placed inside, suddenly the hands move and time begins, not because time itself was created at that moment, but because the mechanism was activated. Some cosmologists wonder if the Big Bang was like placing the battery in the clock, a transition that set time in motion, not the creation of time from absolute nothingness. There is, of course, another possibility, that time is cyclic, looping endlessly with no absolute beginning or end. Ancient myths imagined the cosmos as eternal cycles of creation and destruction, like the seasons turning. Modern physics, in some interpretations, echoes this idea. Perhaps each black hole seeds a new expansion on the other side. Perhaps the Big Bang itself was the echo of a previous collapse. If so, then our universe is not the first or the last, but part of an infinite rhythm of expansion and contraction. These ideas are speculative, but they are not fantasy. They are born of equations, of attempts to reconcile relativity and quantum mechanics, of clues whispered by black holes. Each collapse is a rehearsal of the Big Bang, a smaller stage where the end of time can be studied. By understanding black holes, we hope to understand the origin of everything. And yet, for all our equations and metaphors, there remains a humility in this question. Did the universe begin? Maybe less a question with an answer and more a reminder of the limits of human language. Beginnings and endings are words that make sense within time, but time itself may not yield so easily to such labels. Perhaps the universe simply is, unfolding without absolute start or finish, and our search for a beginning is really a search for meaning. Even so, black holes guide our imagination. They remind us that time can end, that horizons can conceal, that singularities can fold beginnings and endings into one. They are small laboratories of creation hidden inside destruction. To study them is to glimpse, however faintly, the conditions that might have birthed our universe, and perhaps there is a personal echo here. Each of us wonders at some point where our own story began. Was it at birth, conception, in the lives of ancestors, in the stardust that built our bodies? Each answer stretches further back, until finally we reach the universe itself. To ask when the universe began is also to ask when we began, and to sit with that question, even without a final answer, is to participate in the oldest meditation of humanity. So tonight, as you let your breath slow, imagine the universe not as a story with a single first page, but as a library where beginnings and endings blur. Picture clocks without batteries waiting silently on shelves, waiting for some spark to set them ticking. Picture black holes rehearsing in miniature the same drama that unfolded at the Big Bang. Whether or not the universe had a true beginning, whether or not there was a before, one thing is certain. The mystery remains vast enough to hold our wonder, and perhaps that wonder is the real beginning, the spark that keeps the story alive. If black holes remind us of endings, they also awaken one of the most tantalizing questions in physics. Could they lead somewhere else? Could the tunnel of gravity that seems to narrow without end actually open into another world, another place in the cosmos, or perhaps even another universe? It is a thought that has haunted both science and storytelling for decades, and while we must tread carefully, the idea has roots deeper than mere fantasy. In 1935, Albert Einstein and Nathan Rosen considered solutions to Einstein's own equations of relativity. They found that mathematically, two black holes could be connected by a bridge in space-time, a shortcut from one region to another. These theoretical constructs came to be known as Einstein-Rosen bridges, or more commonly today, wormholes. In essence, a wormhole would be like a secret tunnel under a mountain, connecting two valleys that otherwise seem impossibly far apart. To step into one end would be to emerge instantly at the other, regardless of the distance between them. The idea is dazzling, but reality is less cooperative. Wormholes, if they exist at all, appear to be unstable. The equations suggest that they would collapse almost instantly, pinching off before anything, light, matter or traveller could cross. To hold them open would require exotic forms of matter with negative energy density, something not yet known to exist. Without such scaffolding, wormholes remain mathematical curiosities, intriguing but fragile. Still, the possibility lingers, because black holes already stretch our intuition so far. If space and time can be warped into pits so deep that not even light escapes, is it really so impossible that they might also be warped into tunnels? For scientists, the question is not whether wormholes exist in the way science fiction often depicts them. Stable, traversable, doorways waiting to be stepped through, but whether the mathematics of relativity and quantum mechanics might someday allow such structures to exist, even fleetingly, in ways we could probe. An everyday metaphor helps. Imagine two rooms in an old house, separated by thick walls. To go from one to the other, you must walk down the hall, around the corner, through the doorway. But suppose there were a hidden passage, a trap door, a tunnel behind the walls connecting them directly. For most people, the tunnel remains invisible, irrelevant. But for the architect, it is a reminder that houses can hide surprising geometries. Wormholes are the universe's equivalent of trapdoors. Even if we cannot yet crawl through them, the possibility reshapes how we imagine the house of reality. Some theorists even speculate that wormholes could connect not just distant regions of our universe, but entirely separate universes. In that vision, every black hole could be a doorway to another cosmos, invisible to us because the passage lies beyond the event horizon. Matter falling in here might reappear elsewhere, not destroyed, but reborn. To us, from the outside, the black hole looks like an ending. To someone on the other side, if such a someone exists, it might look like a beginning. Of course, we must temper wonder with caution. There is no evidence today that wormholes exist, let alone that black holes function as portals. No traveller has slipped through and sent back word. The mathematics is suggestive, but the physics is harsh. Still, there is value in these speculations because they remind us that black holes are not merely dead ends. They are invitations to imagine what space-time might be capable of beyond our current understanding. In a way, wormholes are less about travel than about humility. They remind us that the structure of the universe may include shapes and passages we have not yet grasped. Just as sailors once feared falling off the edge of the Earth, only to discover the roundness of the globe, perhaps we too are limited by our assumptions. Wormholes ask us to widen our imagination, to allow for possibilities that may one day be tested. There is also a quiet poetry in the idea. Imagine a black hole not as a tomb but as a seed, its collapse not only an end but also an opening. Imagine falling into one and, instead of annihilation, emerging into a new sky, under new stars, in a cosmos that knows nothing of your old home. Science cannot promise this, but the thought lingers, a reminder that even in the darkest physics there is room for wonder, and even if wormholes never prove traversable, they have already given us something. They have enriched our language of imagination, fueled countless stories, inspired artists and writers to picture new worlds. They're examples of how science and creativity are not enemies but companions, each expanding the other. Whether or not we ever find a wormhole to step through, they already connect us to curiosity, to mystery, to the boundless capacity of the human mind. So tonight, as you drift towards sleep, imagine walking through an old house at night, the walls creaking softly. You find a hidden door you never noticed before. It leads to another room, and another, each unfolding into spaces you could not have imagined. That is the dream of wormholes. Black holes may yet be only walls, silent and impassable. But somewhere in their depths the equations whisper of trapdoors, of bridges, of passages unseen. And even if we never walk them, the whisper itself is enough to remind us that the cosmos is not finished revealing its architecture. For most of history, black holes belong to the realm of imagination. They were whispers in equations, strange predictions that seemed almost too outrageous to be real. After all, how do you take a picture of something that swallows light itself? To photograph a black hole sounded like an oxymoron, like trying to capture the outline of silence or the shape of emptiness. And yet, in April 2019, the world awoke to the image of M87 star, the supermassive black hole at the heart of a galaxy 55 million light-years away. It was not sharp, not detailed, not the kind of photograph you might frame on a wall. It was a blurry ring of orange light surrounding a dark shadow. But in its fuzziness lay something profound. For the first time, humanity had glimpsed the horizon of darkness itself. The instrument that made this possible was the Event Horizon Telescope, or EHT, a collaboration of radio telescopes spread across the Earth, from Chile's Atacama Desert to the icy summit of Mauna Kea in Hawaii, from the plains of Spain to the South Pole itself. No single telescope could capture such detail, but by linking them together with precise timing, the EHT team created a virtual telescope the size of our planet. This technique, called Very Long Baseline Interferometry, allowed them to peer into the heart of M87 with a resolution finer than any single eye could achieve. The data took years to gather, and even longer to piece together, but the result was history. An image that confirmed what Einstein's theory had predicted over a century before. When the image was revealed, many people compared it to a blurry campfire seen through fog. At first glance, it looked almost underwhelming, a hazy circle, not the crisp portrait of a cosmic giant some had imagined. But just as a faint flicker of light through mist is enough to tell you there is warmth ahead, the ring was enough to tell us the black hole was real. It was proof not just of theory, but of existence, captured in a frame we could all share. What the image shows is not the black hole itself, but the shadow it casts. Around the event horizon, matter spirals inward, heating as it falls, glowing in radio waves. That glow, bent by gravity, forms a luminous ring. The dark center is the shadow, the place from which light cannot escape. It is a silhouette, a hole in brightness. To capture it is to see the outline of the unseeable. The choice of M87 star was not arbitrary. This black hole is enormous, about 6.5 billion times the mass of our Sun. Its size meant that its shadow was large enough to be detectable from Earth, even across tens of millions of light-years. And yet, the task was still daunting. Imagine trying to photograph an orange sitting on the surface of the Moon, from Earth. That is the scale of resolution required. The EHT team had to synchronize telescopes across the globe to atomic clock precision, record petabytes of data, and then ship hard drives by plane to central locations for processing. Only after years of careful work did the blurry ring emerge, glowing faintly from the darkness. In 2022, the EHT collaboration released another triumph, the first image of Sagittarius A star, the supermassive black hole at the centre of our own Milky Way galaxy. Smaller than M87 star, only 4 million solar masses, it posed its own challenges. Matter swirling around it shifts rapidly, changing over minutes, so the team had to reconstruct the image from shifting patterns, like trying to photograph a candle flame in a breeze. Yet once again the result was unmistakable. A glowing ring, a shadow where space itself curves into silence. These images matter because they transform black holes from abstractions into realities. For decades, we had indirect evidence, stars orbiting invisible masses, X-rays flaring from infalling gas, gravitational waves rippling from collisions. But to see the shadow, to glimpse the outline of the abyss, is different. It is no longer only mathematics, no longer only inference. It is sight, however blurred, however fragile. There is also something deeply human in that moment of revelation. To spend years building telescopes in deserts, on mountaintops at the edge of the South Pole, to gather thousands of scientists across continents, to record mountains of data, all for the chance of seeing a shadow. It is a testament to patience, to collaboration, to the quiet faith that some things are worth chasing even when the chase seems impossible. And perhaps it reminds us of smaller experiences. Think of watching a friend's face through a frosted window, the details obscured but the presence undeniable. Think of hearing a familiar voice crackle through static, distorted yet recognizable. Think of seeing a candle glow through fog. These are not sharp images, but they are enough to carry meaning, enough to assure us that something is there. The first images of black holes are like that. Blurry, imperfect, yet sufficient to prove that what we imagined truly exists. So tonight, as you drift toward rest, picture the ring of M87 star, glowing faintly like embers through haze. Remember that it took the entire Earth working together to glimpse that glow, and let it remind you that even the most impossible seeming shadows can be revealed, given patience, persistence, and a willingness to look. The unseeable is not beyond us. Sometimes all it takes is a planet's worth of eyes turned toward the same darkness, waiting for the moment when it finally blinks back. For most of human history, space was thought of as silent. Look up at the stars, and you see light travelling across vast distances, but you hear nothing. The vacuum of space does not carry sound waves, so the night sky seemed like a concert without music. And yet, in 2015, something extraordinary happened. Instruments on Earth detected a faint signal that changed everything. It was not light but vibration, not photons but ripples in the fabric of space-time itself. Two black holes had collided more than 1 billion light-years away, and the echo of their embrace had finally reached us. For the first time, we had not only seen the universe, we had heard it. The instrument was LIGO, the Laser Interferometer Gravitational Wave Observatory, a pair of enormous detectors in the United States. Each consists of long tunnels with mirrors at the ends, where lasers bounce back and forth, their interference patterns sensitive to changes smaller than the width of a proton. When two black holes spiraled together and merged, they sent a ripple outward, stretching and squeezing space as it travelled. When that ripple passed through Earth, the lasers in LIGO shifted ever so slightly, recording a signal that matched perfectly the predictions of Einstein's general relativity. The sound of that first detection was striking. Converted into audio, it rose quickly in pitch, a short chirp that lasted less than a second. Simple, almost unimpressive to an untrained ear. But within that chirp was the story of two giants, each about 30 times the mass of the Sun, colliding at half the speed of light. The energy released in that final moment was greater than all the light from all the stars in the observable universe combined, yet it passed by us not as fire or explosion, but as a ripple, a vibration that barely stirred our instruments. An everyday anchor may help, Imagine two stones tossed into a pond. As they fall, they create ripples that spread outward, meeting and overlapping. Now imagine that instead of water, the pond is space-time itself, and instead of stones, the ripples are born from black holes spiraling together. By the time those ripples reach the edges, they are faint, barely noticeable, but they still carry the signature of the original event. This is what gravitational waves are: ripples in the cosmic pond, echoes of distant collisions. Since that first detection in 2015, LIGO and its European partner Virgo have recorded dozens of black hole mergers. Each one tells a new story: the masses of the black holes, their spins, the details of their orbits. From these signals, scientists are building a catalogue of cosmic dances, a census of invisible giants. Black holes, once thought impossible to study directly, are now revealing themselves through their collisions. And yet, there is something deeply intimate in these discoveries. The waves travel for billions of years, untouched, unaltered, before brushing past Earth. They are like postcards from the deep past, messages sent before our species even existed, arriving only now. To detect them is to reach across both space and time, to touch the echoes of an ancient event with instruments crafted by human hands. Think for a moment about the delicacy required. A gravitational wave passing through Earth changes distances by less than the width of a proton. To measure it, LIGO uses lasers kilometers long, mirrors suspended and isolated from every vibration of traffic, wind and earthquakes. It is as though we built ears so sensitive they can hear the fall of a feather from across the planet. And what do these ears tell us? That the universe is not silent. It hums with music too deep for ordinary senses, but not too deep for imagination. There is also poetry in the signals themselves. Each chirp is unique, like a note in a cosmic symphony. Some are higher, some lower, some last longer, some shorter. Together they form the beginnings of a new astronomy, an astronomy of sound rather than sight. For centuries we have studied the universe with telescopes gathering light. Now, with gravitational waves, we can listen as well. We can see and hear the cosmos, adding harmony to vision. Perhaps this is why the discovery resonated so deeply. It was not just the detection of black holes colliding. It was the dawning realization that the universe is richer than we thought, offering us senses we had not yet used. Imagine living your whole life in silence, then suddenly hearing music. That is what 2015 was for astronomy. The first note in a song the cosmos has been singing all along. And there is more to come. With every detection we learn not only about black holes, but about the history of the universe itself. We learn how often stars collapse into black holes, how galaxies grow, how matter moves on the larger scales. We may even one day hear gravitational waves from the Big Bang itself, the faint hum of creation still echoing through space-time. So tonight, as you rest, imagine those ripples spreading endlessly across the cosmic pond. Imagine them brushing past your pillow, through your body, unnoticed except by the most sensitive instruments. Imagine the chirp of two black holes colliding, a fleeting note that travelled 1 billion years to reach us, carrying with it the memory of a cosmic dance. The universe is not silent. It is filled with music too vast for ears, too faint for casual notice, but always present, always singing. And we, at last, have learned to listen. When we think of black holes, it is tempting to imagine them as exotic intruders, as strange monsters lurking in corners of the galaxy. But in truth, they are not outliers. They are the natural outcome of stellar life cycles, the final chapter written into the story of massive stars. To understand them, then, is to understand not only the drama of collapse, but the quiet inevitability of cosmic evolution. Every star is a balancing act. Inside, nuclear fusion burns hydrogen into helium, releasing light and heat. That energy pushes outward. a steady pressure that counters the inward pull of gravity. For billions of years, this balance holds. The star shines steadily, like a candle protected from drafts, its flame calm, its structure secure. But eventually the fuel runs low. When the hydrogen is gone, heavier elements begin to fuse, helium into carbon, carbon into oxygen, and so on step by step, like a fire consuming whatever wood remains in the pile. Each stage grows shorter, more frantic, until finally the star can fuse no further. Iron is the last stop. It does not release energy when fused, so once the core fills with iron, fusion halts. The outward push fades, and gravity, patient and relentless, takes over. For stars like our Sun, the collapse ends more gently. The outer layers drift away into space, forming planetary nebulae, while the core stabilizes as a white dwarf. For stars more massive, 3, 4, or more times the mass of the Sun, the collapse is violent. Gravity crushes the core beyond the point where atoms can resist. Protons and electrons merge into neutrons, forming a neutron star, so dense that a spoonful of its material would outweigh mountains. And for stars even heavier, there is no stopping point. Gravity overwhelms all resistance, compressing the core into a singularity. A black hole is born. There is something both terrifying and beautiful in this. A star that once shone with brilliance, perhaps with planets circling and moons reflecting its light, ends by folding into darkness. Yet this darkness is not failure. It is transformation. The black hole is not the star's erasure, but its continuation, the form gravity always intended once fuel was gone. An everyday metaphor may help. Think of a candle burning. At first, the flame is bright, steady, feeding on wax. As the wax dwindles, the flame flickers, smaller, weaker, until at last it gutters out. The wick remains, charred, but present. The light is gone, but the material has not disappeared. It has simply changed. So too with stars. Their light ends, but their substance continues, either as white, dwarfs, neutron stars, or black holes. And like candles, stars are not solitary events. Their endings feed the beginnings of others. When massive stars explode as supernovae, they scatter heavy elements into space: carbon, oxygen, iron, gold. These atoms enrich gas clouds, which collapse to form new stars and planets. The iron in your blood, the calcium in your bones, the oxygen you breathe, all were forged in stellar furnaces and scattered by stellar deaths. Even black holes, by their gravity, shape the galaxies that nurture new generations of stars. Endings in the cosmos are never absolute. They ripple forward, seeding new stories. It is important to remember too that black holes are not rare. They are sprinkled throughout the galaxy, the natural tombstones of massive stars. Some roam alone, dark wanderers invisible except for their pull on nearby stars. Others gather in binaries, drawing matter from companions, glowing in X-rays as the material heats and spirals inward. And at the hearts of galaxies, supermassive black holes loom, their origin still mysterious, but their presence undeniable. To speak of black holes is not to speak of exotic anomalies, but of the expected outcomes of stellar lives. This recognition reshapes our view. Black holes are not intrusions into the cosmic order. They are part of it. They are chapters written into the script, punctuation marks as natural as the commas and periods in a sentence. A universe without black holes would be incomplete, its cycle of birth and death broken. And perhaps there is something comforting in this. Just as the seasons turn, just as leaves fall to enrich the soil for new growth, stars collapse to enrich the cosmos for new beginnings. Black holes are not the end of the story, but part of the rhythm of it. They are the quiet pauses between verses in the cosmic song. So tonight, as you think of stars overhead, Remember that some of them are nearing their ends. Some will collapse into neutron stars, some into black holes, and when they do, their matter will not vanish, their story will not be erased. It will be folded into the universe's continuing song, stored in gravity's memory, waiting to shape what comes next. Black holes are endings, yes, but endings that flow naturally into beginnings. Candles that burn down into embers, feeding warmth into the night even as their flames fade. When we speak of time in daily life, we usually imagine it as something flowing. A river carrying us forward, moment after moment. The past drifts behind, unreachable but remembered. The future lies ahead, invisible but anticipated. The present feels like the only shore we can stand upon, a fragile ledge between what has been and what will be. This is the intuition of presentism, the belief that only the present truly exists. The past is gone, the future unreal, and all that is real is now. Yet physics has long suggested another possibility, one that feels at once disorienting and strangely serene. In Einstein's relativity, time and space form a single fabric, space-time. Events are not created and destroyed as we move through them. They simply are, like points written on a map. From this view, often called eternalism, the universe is like a block, a vast four-dimensional structure where all moments, past, present and future, already exist. We do not move through time as through a river. We move along paths in the block, experiencing slices of it in sequence. The past is still there, the future is already there, the whole is complete. This block universe view is unsettling at first, because it seems to erase our sense of freedom. If the future already exists, is everything predetermined? Are we just passengers following a script already written? But it can also be comforting. If the past is still there, then nothing is ever truly lost. The laughter of a child long grown, the voice of someone gone, the warmth of a summer long past. These are not annihilated but preserved, written into the coordinates of space-time, even if we can no longer visit them. The philosopher Augustine once wrote, in the 4th century, that he understood what time was until someone asked him to explain it. Then it slipped away. If no one asks me, I know. If I try to explain, I do not. His paradox still echoes today. We live so intimately with time that we rarely question it, and when we do, it dissolves into mystery. Black holes, with their peculiar treatment of time, force us to confront this paradox directly. At the horizon of a black hole, two observers can disagree radically about the same event. For the one falling in, moments pass normally. For the one watching from afar, the same moments appear to stretch into eternity. Which is the true now? In a block universe, both are true. The falling and the frozen coexist, written into different slices of the four-dimensional whole. Reality is not one unfolding present, but many simultaneous layers. An everyday analogy might help. Think of a book. To the reader, the story unfolds page by page. To the author, or to someone holding the closed volume, the entire story already exists at once, beginning to end. The reader experiences a present, but the book is a block, with every chapter equally real. The universe, eternalists suggest, is the same. We are readers, experiencing pages in sequence. The cosmos is the book, complete in its entirety. There are, of course, counter-arguments. Presentists insist that the future cannot be real until it happens, that to say it already exists is to strip meaning from becoming. They argue that our choices matter because they shape what has not yet been written. Eternalists reply that our choices are part of the block too, woven into the fabric just as much as mountains and stars. The debate continues, as lively in philosophy as it is in physics. Black holes tilt the argument. In their strange bending of time, they reveal how slippery now can be. If one observer's present is another's eternity, then perhaps presentism falters. The block, with its many overlapping realities, seems to fit better. and in accepting the block we may find a peculiar peace. Imagine for a moment your own life as a line drawn through the block universe. Every moment you have lived, every moment you will live, already part of that line. You're not a fleeting spark burning out, but a curve etched permanently into space-time. You cannot return to earlier points nor jump ahead, but they are all there, part of the grand tapestry. To think this way is to see your life as a whole, not just a vanishing present. It is to recognise permanence where we usually feel only loss. This perspective does not answer every question, nor erase the poignancy of passing, but it does suggest that what we call now is not the only reality. It is simply the slice we inhabit, the page we're reading, while the rest of the book waits quietly. And perhaps black holes, with their horizons stretching time into strange shapes, are reminders of this truth, that reality is larger than our present, that now is a thread in a far greater weave. So tonight, as you close your eyes, picture the universe as a vast library of moments. Every instant, past dinners, future dawns, the first heartbeat, the last, written already, preserved like ink on a page. You're walking the shelves, pausing to read this one, while others wait in quiet order. Black holes, those guardians of horizons, show us that time is not only a river but a structure, not only a flow but a map. And in that map, we're already whole. There comes a moment at the end of every long exploration when the facts and equations begin to fade into something quieter. You may not remember the names of every physicist we spoke of, or the exact numbers of masses and distances, or even the order in which the ideas unfolded. And that is perfectly fine. What lingers instead is a feeling. The sensation of having walked a long road together, of having looked into shadows and finding not fear, but wonder. Black holes began in this journey as monsters, devourers, incomprehensible abysses. They seemed at first like the villains of the cosmos, places where even light could not survive. Yet, as we wandered more slowly, we found something different. Black holes were not only endings but maps. They were teachers, revealing how gravity, quantum mechanics, and thermodynamics meet in ways nothing else can reveal. They whispered of information not lost but hidden, of horizons that store secrets like pages of a book, of time itself as something emergent, perhaps even illusory. And in those whispers, we discovered that black holes are less like destroyers and more like guides. Maps made not of ink or parchment, but of darkness. Maps that point us toward the deepest truths about reality, truths we cannot yet fully translate, but whose shapes we can trace. An everyday image might help. Imagine walking at night with only a lantern. The trees ahead are shadows, the path uncertain. Yet sometimes it is the very darkness that guides your steps. The lantern casts the shadows you need to see the way, to notice the bends and roots. Black holes are like that. Their darkness is not an obstacle but a contrast, making visible the structure of the universe itself. By studying what we cannot see, we learn what reality is made of. Time, too, has revealed itself differently along the way. Once thought to be fundamental, perhaps it is instead a melody emerging from deeper notes, a film strip unspooling frame by frame, a thread woven by entanglement. Black holes bend it, stretch it, freeze it, teaching us that now is not as absolute as we believe. And yet, in that strangeness lies a quiet reassurance. Time may be a structure more permanent than our fleeting experience suggests. Every moment, past, present, and future, written into the block of the cosmos, as permanent as stars. What began as fear of singularity is turned into curiosity about beginnings. If black holes end in singularities, and if the universe began in one, perhaps the two are mirrors. Perhaps endings are not endings at all, but folded pages pressed against beginnings. Perhaps in each collapse the cosmos rehearses creation itself. And finally, when we looked outward, not at theories but at evidence, we found that black holes are not distant myths. We have photographed their shadows. We have heard their collisions. We have traced their births in the deaths of massive stars. They are not exotic strangers. They are neighbours, part of the natural rhythm of galaxies. And in their quiet inevitability, they remind us that the universe is not chaos but cycle, not destruction but transformation. As we stand now at the edge of this journey, the details blur into something simpler. Black holes are guides. They are reminders that darkness can reveal as much as light, that silence can carry as much truth as sound, that endings can fold into beginnings. They show us that the universe itself may be far stranger, far richer, and far more elegant than our language can capture. And so, we close not with equations, but with an invitation to see black holes not as terrors, but as companions in our search for meaning, to let their shadows remind you that even the unknown has structure, even the mysteries hold maps, to sleep tonight with the comfort that you are part of this vast story, woven from the same fabric as stars, moving gently along the currents of time. Imagine yourself drifting now, as though floating in a quiet river. The water is smooth, the current soft. Around you, night gathers, but it does not press, it carries. Time itself is that river, flowing past you, carrying you not toward an end, but into the continuity of all things. Black holes, with their dark horizons, sit on the riverbanks, silent markers of how the flow bends, how the story deepens. You drift past, unhurried, unafraid. Maps made of darkness. That is what black holes leave us. Not directions we can follow just yet, but outlines we can trace, knowing they lead somewhere meaningful. And as you close your eyes, perhaps you will feel the truth not as a statement, but as a presence, that the universe is both stranger and more intimate than we can know, that even its shadows are guides, and that in this great unfolding you are exactly where you belong. So let yourself rest. Let the questions drift. Let the quiet carry you. The stars are still shining. The black holes are still waiting. And time, whatever it truly is still flowing gently around you, like a current that asks nothing more than for you to float, to breathe, to dream.